morning children, and welcome back to your chemistry class. So we had already begun with a new chapter, that is electrochemistry, and yesterday in this chapter we had studied about the standard electrode potential, we studied about the electrochemical series, right? So moving ahead, we had discussed yesterday certain factors that affect the standard electrode potential. What were they? They were the nature of the metal, the concentration of the ions, and even it depends upon the temperature. Temperature, that is 298 Kelvin or 25 degrees Celsius should be the temperature, right? However, sometimes what happens, these standard factors like your temperature and concentration, they are not obtained. Then the electrode potential cannot be directly obtained from the electrochemical pattern that we had studied yesterday, right? So in such cases, the electrode potential of the electrode assembly, it can be calculated by a very important equation which is called as Nernst equation, right? So for an electrode involving process of reduction, then your E will be equal to the standard reduction potential minus RT upon NF log E reduced state upon oxidized state. Okay, oxidized state. So when is this obtained? This equation is used for an electrode which involves the process of reduction. Okay, for electrode which involves the process of reduction. Clear? Now, for an electrode which involves process of oxidation, what will be the equation then? Then your E will be equal to the standard electrode potential minus RT upon NF log E. It will be oxidized state upon the reduced state. Fine. So when do we use this formula? For electrode which involves oxidation. I hope till here it's clear. So let us understand what is E. It is either your reduction or your oxidation potential, right? E naught, it is the standard reduction potential of the same electrode assembly, right? Then what is your R? It is the gas constant. What is the value of the gas constant? The gas constant value is 8.314 joules per Kelvin per mole, right? Then what is this T? T is the temperature of the electrode assembly. F is the 1 Faraday. So what is 1 Faraday? 1 Faraday is equal to 96,500 coulombs. Okay. And what is your N? N means over here the number of moles of the electron transferred. So I hope you have understood this point. And what does this oxidized state mean over here? Concentration of the substance undergoing reduction, remember. And what is the reduced state means over here? The concentration of the substance undergoing oxidation. This point is clear. Let me write it down so that you remember. Reduced state and oxidized state. What do they mean? So reduced state means the concentration of the substance undergoing oxidation, right? And oxidized state means concentration of the substance undergoing reduction. Clear? So now for the electrode reaction, how do we write down? Let's see. So for electrode reaction, let's see, if we take any cation in the aqueous state, it will accept the number of electrons and it is going to give us the metal which will be in its solid state. Clear? Thus the electrode of the cation to the metal form will be equal to what? E naught, the cation to metal form, minus RT upon NF log E. This is the metal in its solid state, right? Upon the metal in its ionic state. Is this point clear? Now, remember, when it is in the solid state means it is the reduced state, and when it is in the ionic state it is the oxidized state. Followed? So the simple equation of Nernst equation, it can be used if our temperature that we take is 298 Kelvin, right? But the concentration is not standard. Then in that case, E will be equal to E naught cell minus 0.059 upon N log 10 1 upon M, the ionic form which is in its aqueous state, right? So this is for reduction of electrode at 298 Kelvin. For reduction electrode at 298 Kelvin, right? Now for oxidation, this one, for oxidation electrode at 298 Kelvin, let's see, then the standard electrode potential minus 0.059 upon N log the cation in its aqueous state, right? So this is the formula we are going to use. So for reduction electrode potential, this, for oxidation reduction potential, this, and now we are going to talk when redox reaction is there, then which formula are we going to use. So when it is a redox reaction, then what do we do? So let's take an equation like AA plus BB gives CC plus DD. So these small alphabets are the number of moles, okay? So now your reduction cell will be equal to the standard electrode potential minus 2.303 RT upon NF log to the base 10 product upon the reactant. Okay, so let's write it down. This will be equal to E naught cell minus 2.303 RT upon NF log to the base 10. What is your product? Product is C to the power of C D to the power of D upon A to the power of A B to the power of B, right? This can also be written as what? This can also be written as E cell is equal to the standard reduction potential minus 0.059 upon N, right? When we have calculated, you don't have to learn the complete calculation. You straight away have to just learn the formulas over here. So log to the base 10 C to the power of C D to the power of D upon A to the power of A B to the power of B. So this can be the equation that we can use. Clear? Now when reaction is said to be in equilibrium, just now what we have done, when it is a redox reaction, then this is the formula that we use, right? When the reaction is said to be in equilibrium, then what do we do? If the cell gets short circuited, understand, when is the cell said to be in an equilibrium? When is the reaction said to be in equilibrium? So when the cell gets short circuited, then the flow of electron continues till there is potential difference between the two electrodes. Fine. But when there is no potential difference, then the reaction is said to be in equilibrium. So when reaction is said to be in equilibrium, then as I said that when the cell gets short circuited, then the flow of electrons still continues till there is potential difference, right? But between the two electrodes. But when there is no potential difference, then the reaction will be said to be in equilibrium, which is represented by K and C. This is your equilibrium constant. This is C, okay? This is C. This is called as equilibrium constant, right? So your equilibrium constant will be equal to what? C to the power of C, D to the power of D upon A to the power of A, B to the power of B. Clear? Therefore, your reduction potential will be equal to what? The reduction cell, standard reduction cell minus 2.303 RT upon NF log to the base 10, the equilibrium constant. This can also be written as E cell is equal to standard reduction potential minus 0.059 upon N log to the base 10 equilibrium constant, right? Now this E cell is 0. This is equal to the standard electrode cell minus 0.059 upon N log to the base 10 equilibrium constant. Therefore, log to the base 10 equilibrium constant will be equal to what? N standard electrode cell upon 0.059. Clear? Therefore, we can also say, if we need to remove this log, then we can also say that the equilibrium constant is equal to anti-log N E naught cell upon 0.059. Okay, so we can say that the equilibrium constant is equal to anti-log into number of moles of the electron transferred into your standard electrode potential upon 0.059. Clear? I hope till here things are clear. Now, based on this, we are going to do some numericals. Let us understand certain numericals. The question says, calculate the standard electrode potential of nickel ion to nickel electrode if the cell potential of the cell is given like this: nickel to nickel ion 0.01 capital M. Then the other cathode is copper ion with the concentration 0.1 molar, right? And it's given copper is 0.59 volts. Now, what is given to us? Let's see. Given to us is the copper ion to copper electrode potential, that is 0.34 volts, right? The cell reaction, let us write down. The cell reaction is nickel, which is in its solid state, plus it's the copper ion, right, which is in its aqueous state, gives copper, which is in the solid state, plus nickel ion, the aqueous state. So now let's use the equation. E is equal to the standard electrode potential minus 0.0591 upon N log 10 nickel ion upon the reactant, that is copper ion, right? So 0.59 is equal to E naught cell minus 0.0591 upon number of molecules are how many? 2 log to the base 10, 0.01 upon what is the concentration of copper ion given? 0.1, right? Therefore, E naught cell is equal to 0.569 minus 0.0295. You solve this, you will get this equation. Now this will be equal to 0.5395 volts. Followed? Now let me come over here. E naught cell is equal to what? The cathode reduction potential minus the anode reduction potential, right? So what is the value that we got over here? 0.5395 is equal to 0.304 minus EA, or we can say EA is equal to 0.304 minus 0.5395. I hope you all can see till there. I don't know. This is equal to minus 0.2355 volts. So we have calculated what? The standard electrode potential of the nickel ion to nickel electrode is what? Minus 0.2355 volts. Clear? So this is your answer. Let's do another question. Let's do the second numerical. It says calculate the value of the E cell at 298 Kelvin for the following cell. So let us look at this cell. Aluminium 2, aluminium ion, right, Al3 plus, concentration 0.01 m, to the cathode, that is Sn2 plus, concentration 0.015 m, to the metal Sn, right. It's given that the standard electrode potential of aluminium ion to aluminium is minus 1.66 volts. So this is your anode, clear? And that of tin ion to tin, it is minus 0.14 volts. So this is your cathode, this is your cathode, this is your anode, right? So what formula are we going to use over here? E naught cell is equal to the electrode potential of the cathode minus the standard electrode potential of anode. So this is equal to minus 0.14 minus what? Minus 1.66. So this is going to give us 1.52 volts. Okay. Now let's see, the E cell is equal to E naught cell minus 0.0591 upon N log, what was the formula? Product upon the reactant, right? So now over here we are going to check the valencies. See, the valencies are different. So let us first balance the valencies. So aluminium is losing 3 electrons to become aluminium 3 plus, correct? And tin is accepting 2 electrons to become Sn. So the valencies have to be balanced. So this one can be multiplied with 2. And the second equation, this is the first equation, then the second equation can be multiplied with 3. So what are we going to get? We will get 2 aluminium plus 3 tin ions. This is going to get cancelled. 3 2s are 6, 3 2s are 6. The electrons will get cancelled. This is going to give us 2 aluminium ions, cations of aluminium, plus 3 molecules of tin. This is what we are going to obtain. Clear? Further, cell is equal to 1.52 minus 0.05912 upon 6. Okay. Log 10 aluminium ions power 2 upon tin ions into 3. So this will be equal to 1.52 minus 0.05912 upon 6 log 10. What is the concentration that was given in the question for aluminium? It was 0.01. Okay, to the power of 2 upon tin concentration, ion concentration was 0.015 to the power of 3. So when you solve this, what does it become? 1.52 minus 0.0145, and this is going to give us 1.5055 volt. So over here the value of the electrode potential is equal to 1.5055 volts. So this is how we are going to do the numericals. I will be sending some of the numericals for your register work. Now let us talk about Gibbs free energy and EMF of a cell, right? Now in case of electrochemical cell, what do we know? That the electrical work done, it is always equal to minus the number of moles of electrons transferred into F into the EMF of the cell. Clear? Now, how did we get this? We know that work done is equal to charge into EMF, right? So, what if the charge is equal to minus NF into EMF? How do we write down? E cell. So, this is what I have written over here. Minus NF into the EMF cell, right? So, always remember this is equal to decrease in the free energy, right? For comparing different cells, then standard cell potential, that is E naught, is always used. Followed? Now the free energy change, that is delta G naught, it is represented how? This will be always written as delta R G naught is equal to minus NF into the EMF cell. Clear? Now we know that this EMF cell is equal to how much? 2.303 RT upon NF log equilibrium constant, isn't it? So this is what it is. Now what is the relationship between Gibbs energy and equilibrium? So we know that Gibbs naught is equal to minus NF 2.303 RT upon NF log to the base 10 equilibrium constant. Therefore, we can say that Gibbs energy is equal to this is Gibbs R, delta R energy will be equal to minus, what is this? 2.303 RT log to the base 10 equilibrium constant. Okay. I hope this is clear. Now, I have already told you what is your delta R G naught. It is minus NF into EMF of the cell, right? And delta G naught is this. So, what will be your delta R G naught? The real Gibbs energy change will be equal to minus 2.303 RT log to the base 10 equilibrium constant. Now let us understand metallic and electrolytic conduction. So from electrical point of view, substances that can be of two types, either they are electrical conductors or they are the insulators, right? So what are your electrical conductors which allow the current to pass through them? For example, there could be metals, they could be of fused ionic compounds, they could be gases at low pressure, etc. Right? And what are your insulators? They do not allow the current to pass through them. For example, they could be rubber, plastic or sulfur. Thus, the flow of current is either due to flow of electrons or due to flow of ions. I hope this much you know. So, flow of current is due to either flow of ions or flow of electrons, right? So let us understand first the flow of electrons. Now such substances, they are called as metallic conductors, and the phenomenon is termed as metallic conduction, which allow current to pass through them due to the flow of electrons, right? Over here, no chemical change takes place, and thus we say that metallic conduction, it decreases with the increase in temperature. Clear? Now next we talk about the flow of current due to ions. So such substances which allow the current to pass through due to the flow of mobile ions, they are called as electrolytic conductors, and the phenomenon is termed as an electrolytic conduction. Clear? So chemical change takes place over here during the flow of the current. They also allow current to pass through them, either they in the fused state or they are in the aqueous state, but they never allow the current to pass if they are in their solid state. Why so? Because the ions are closely packed and they do not have free mobile ions to allow the current to pass through. So the ions, they move to opposite charged electrodes. I hope you know that the positive charges are going to move towards the negative electrode and the negative charges are going to move towards the positive electrode, right? And next important point is that in electrolytic conduction, it increases with the increase in temperature. The metallic conduction, it decreases with the increase in temperature, but electrolytic conduction, it increases with the increase in temperature. Clear? Now if we classify the electrolytes, why I'm not writing it down much, because I know you have already studied this number of times. So just going to give you a review of whatever we have studied. Next, let us talk about the classification of the electrolytes, right? So you already know either they are strong electrolytes or they are the weak electrolytes, right? Now what are the factors which affect the electrolytic conduction? What are the factors? Now we are going to understand that affects the electrolytic conduction. So first factor is the nature of the electrolyte. Okay, the nature of the electrolyte. So remember over here the solute-solute interaction is very high. Less dissociation of the electrolyte happens in the weak electrolytes. Then solute-solute interaction is less, more dissociation, and then it is said to be a strong electrolyte. Right? Now let's talk about the next important point. Next factor is solvation of ions. What do we mean by solvation of ions? That is solute and the solvent interaction. So over here, higher the interaction, greater will be the solvation of the ions, and less current is conducted by the ions, then less interaction is there, then the less solvation of the ion takes place and more current is conducted by the ions. Clear? Once again I repeat, what do I mean by solvation of ions? Firstly, what does this word solvation mean? Over here it means solute and the solvent interaction. So higher the interaction, greater will be the solvation of the ions. Less current is conducted by the ions, right? Lesser is the interaction, lesser will be the solvation of the ions, and more current will be conducted by the ions. I hope this point is clear. Then third point, the third factor on which it depends upon is the viscosity of the solvent. Okay, so solvent solute interaction, larger the interaction, greater will be the viscosity and less will be the electrolytic conduction. I repeat for viscosity of the solvent again, larger the interaction between the solvent and solute, greater will be the viscosity and less electrolytic conduction will take place. Okay, let's talk about the fourth point, that is the nature of the solvent and the concentration of the solution, right? Now remember, over here the polar solvents, they show greater dissociation of ions. Okay, what did I say? Polar solvents, they show greater dissociation of ions. Higher concentration, less will be the dissociation of the electrolyte into the ions and less current is going to flow. I repeat, higher will be the concentration, lesser will be the dissociation of the electrolyte into the ions, and there will be less current flowing because the ions formed are less, or the dissociation is less, therefore less current is flowing through it. And lastly, temperature. The electrolytic conduction, it increases with the increase in temperature. This I had already told you before. So electrolytic conduction, it increases with the increase in temperature. So I stop over here. In the next video, we will be talking about some basic concepts that are further related to the electrolytic conductance. Thank you.